Hope everybody's doing well today. We are going to start on chapter 8 today, which is on elimination. So before we do that, are there any questions about where things are, moving forward, any of that sort of, excuse me, any of that sort of stuff? Okay, so the scores, I don't know if you got the announcement I just sent out. The scores on Canvas are curved. There was a 6-point curve on the exam. At this point, if you want to start sort of seeing where you stand moving forward, your grade is going to be exam 1. Oops, let me share that screen. Can't see the math otherwise. Okay, so exam, oh, that light is terrible. Let's turn on something else. Okay, that's a little better. Okay, so exam 1 times 0.2 plus exam 2 times 0.2. Now over the next thing, what I want y'all to do is, if you are participating in the discussions, so discussions are going to end up being 100 times 0.1. So if you know you've missed one discussion, make this an 80. If you've already. So if you know you've missed 2, make this a 60. Okay. So this is the discussions. For Alex, assume you're going to finish it all the way up and get 100 times 0.1. Okay. And then put in 2x. So this is going to be, just say exam 3 and the final. So just for right now, just say, what do I need to get on exam 3 and what do I need to get on the final? Assuming you keep both of these 2 grades. And then you need to set it equal to the lowest score that is in the bracket for the grade you want. So if you want a 90, set it, or an A, set it equal to 80. If you want a B, 80. C, 70, and so on down the line. Okay, so take your score, and then discussion, Alex. And I know some of you have emailed me about issues with Alex, like you take a knowledge check and you think you're at 60 and then it brings you down to 57. Don't worry about it. Okay, I'm still working through the program and trying to figure out how everything fits together, so don't worry about it. Just plan that you're going to finish it and that you'll earn all 100 points. And that'll be a good way to sort of see where you are. Oops, that's not what I wanted to do. Okay. All right, so you can take that and kind of see where things stand. Are there any questions about that? Okay. All right, so we're going to move into chapter 8. And chapter 8 is, it's a chapter on alkenes. So alkenes are functional groups that have carbon-carbon double bonds. We're going to talk about structure of alkenes and preparation. So the structural part and naming, that'll come first. The preparation is through 2 mechanisms, both that are called eliminations. So just to sort of give you an idea, of where we're going with this, and to sort of help prime you for high levels of organization, I want you to consider this substrate. Okay, so bromocyclohexane. Okay, it's achiral. It's a secondary alkyl halide. Okay. Now what we're going to do is we're going to treat it with a reagent. And in the, if you have the notes, it says sodium hydroxide, but I just want you to write a reagent right now. Okay. And there's two things that can happen. If the reagent acts as a nucleophile, you're going to get, that R is reagent, you're going to get a substitution product. And that product, because you don't have a lot of details over here and it's a secondary, this could go by SN1 or SN2. Sorry, sorry, I was pulled up notes and then I looked at them and that's not exactly what I saw. Okay, if instead the reagent is a base, and for base, we're just going to write B. Okay, so B is base, not boron. Okay. If the reagent acts as a base, then what you're going to get is an elimination product. That can be formed by one or two different mechanisms called elimination E1 and elimination E2. Now this 1 and this 2 mean the same thing as this 1 and this 2. So E1, that's a 2-step elimination. E2 is a 1-step elimination. So a few things that I want to write on here. Okay, so a nucleophile. Okay. Nucleophiles, whether they're strong or weak, as a, well here, let me write it like that. Okay, strong or weak nucleophiles, those attack positive carbocations and partially positive carbons. Okay. That's what their job is to attack a carbon. Okay. When your job is to attack a carbon, this is a kinetic effect or kinetic behavior. How quickly does your nucleophile attack your carbon sites? Now, the base has a totally different job. Base can be negative with a lone pair or just have a lone pair. But the job of the base is to grab protons, okay? Not carbons. So nucleophilic behavior is going after carbons. Base behavior is going after protons. Grabbing protons is not kinetic, that's a thermodynamic behavior. Okay, and thermodynamics is related to equilibrium. Okay. Now, one other thing I want to put on here, and then I'm going to erase and just deal a little bit with this substrate, is that I want you to right away remind yourself that substitution reactions are very dependent on the solvent. So in this secondary substrate, if you want an SN2 reaction to take place, then you have to use a polar aprotic solvent. For the secondary substrate, if you want SN1, you have to use polar protic. So if you use the wrong solvent, the reaction won't proceed in the way in which you are planning it to. So they're very dependent on the solvent. Eliminations, these are not picky about solvent. I'm going to have to get some new markers. These are starting to write too fast. Okay. So are there any questions so far before we talk a little bit about some issues with the substrate that we have to have in order for elimination to take place? Okay. So I'm going to erase some of this stuff. Okay. All right. So if you look at this elimination pathway from here to here, when you have an elimination, your product is going to be an alkene. Okay. An alkene requires you to have a carbon-carbon double bond, which means you have to have 2 carbons at a minimum in your substrate. So for elimination to occur, you need a minimum of 2 carbons. Okay, so that's requirement number 1. Okay. Now, if you look at your substrate, this carbon in blue is the one with the leaving group. That's carbon alpha. So you must have carbon alpha with a leaving group. And just like for substitutions, you need a good leaving group. You need something that will leave. Okay. Next door to alpha, you have in red beta. Now in this particular substrate, there's 2 beta carbons. Okay. But beta carbons have to have a minimum of 1 hydrogen. Okay. So your carbon beta must have hydrogens. Okay. So that the base can come and take one of these protons, and in this case, since it's symmetric, it doesn't matter. Take one of these protons and cause the elimination reaction to take place. Okay. Again, it should be noted that carbon alpha needs to be sp3. We are only going to be doing elimination in, on alkyl carbons, not vinyl carbons. All right, are there questions about where we're going before we talk a little bit about naming? Okay. All right, so 8.3. This is nomenclature of alkenes. Oops. Sorry. Okay, so a lot of the rules that you used already in naming alkanes and cycloalkanes still hold true here. These are just some like amendments. The first amendment is that when you have an alkene, the ending changes from ANE for alkanes to ENE for alkenes. Okay. So this will be the last thing you write, ENE. The second thing is that you're going to find your parent chain but it must include the double bond, because an alkene has a higher priority as a functional group than an alkane. So the name of your compound has to include that pi bond. Okay. So then you're going to number your chain. Okay. So that the double bond gets the lowest number possible. Okay. The double bond numbering is more important to be lower than numbers for substituents. Okay. The last rule is that the numbering or the position of the double bond is given by one number. Which is going to be the first carbon that's participating. And I'll give you an example of that, and then we'll do a larger compound. Okay. So let's say we are going to look at this compound. If we number from left to right and right to left, the pi bond either starts at 2 or it starts at 1. Okay, so since 1 is a lower number than 2, the blue numbers are the better numbers. So if we name this and we're saying that our origination point, the first carbon that participates in the double bond is carbon 1, you don't have to say that it goes to carbon 2, it's implied. It goes from 1 to 2. So this would be 1 propene. So let's do a bigger example, unless there's anybody that needs these rules, or if I'm going too fast on the rules. Okay. So the compound we're going to look at is this one. So we first have to find our longest chain. And we'll just, if you go 1, 2, 3, 4, 5, 6, you're going to get an isopropyl or a branch substituent. Remember, we want more simple substituents than fewer branch substituents. The more simple, the better. So 1, 2, 3, 4, 5, 6, 7. So this is a 7-carbon parent chain. If you number from left to right, Now you could make this one up here carbon 7. That's fine. So you're still going to have a methyl on 6. Whether you go up or down, it won't matter. Okay. The blue numbers have the pi bond originating on carbon 2. If you numbered from right to left, it would end up on carbon 5. So 2 is a lower number than 5. So the numbers that we have listed on this alkene are correct. Okay, now we identify our substituents. So we have a methyl at carbon 5, another methyl at carbon 5, and a methyl at carbon 6. So those are the identities of our substituents. So we have 3 methyls. So we're going to write our numbers as 5, 5, 6. Since I have 3 numbers, I need the prefix tri, methyl. And now I have to give the position of the pi bond to, with a 7 carbon parent, heptene. Okay. Now, this is the old way that IUPAC rules named alkenes. The new way is similar, 5,5,6, trimethyl, and then you go straight to your carbon chain, hept, and then in the middle of the alkene name, you put the position and then ENE. So this is old, this is new. Both are correct. When IUPAC introduced the new terminology, it was adopted by almost every country except the United States. So the US still uses this numbering and this naming. Most of the rest of the scientific community uses the new. Okay, so if you move on to 212, I'm pretty sure Dr. Barrio Sosa uses the new method. I use the old method, but they're both correct. Okay. Right, now there are some simple alkenes that have stuck in terms of like they don't use IUPAC names. So the old name for this, which is still used, is ethylene, propylene, instead of 1-propene. This is an appropriate name. And then if you have an aromatic ring, and then in conjugation, this is called styrene. So you should flashcard put those on. Okay. Now, there are some alkene substituents that you can have off parents that also have common names. So if the parent is going to be the box, and then if you come out and you have a group that looks like this, it's called a vinyl group. That's an allyl group. Phenyl group. Methylene group. Okay. And again, I think for these 7, they should just go on flashcards. Are there questions about how to name or the historically relevant and common substituent names? Okay, let me write a little box over here. This is not supposed to look like cyclobutane. This is just representing a parent. I didn't think about that when I drew it. Okay, so we're going to talk a little bit about substitution of alkenes. So, let's see, alkene, degree of substitution. So we're going to have 4, so R, two. If it's not drawn, it's a hydrogen. Okay. So you can have 1 R group, 2 R groups, 3, and 4. So the first is called monosubstituted. Disubstituted. Trisubstituted. Substituted. And tetra substituted. Okay. In terms of stability, stability of alkenes increases in this direction. Now, in terms of naming, monosubstituted, these are the easiest to name, and you just use the rules that we looked at on the last slide. Okay. If you get to disubstituted, you can use relative stereochemistry. So remember, relative stereochemistry is cis and trans. Absolute stereochemistry is R and S. So you could have your 2 R groups on the same side. If you draw a line across your pi bond like this, if your 2 R groups are on the same side, that's cis. If they're on opposite sides, if you draw your line across, they're trans. And just like with the disubstituted cycloalkanes, you have to include cis or trans in the name. Okay. Now the trisubstituted and the tetrasubstituted, you cannot use, or you should not use, cis and trans. What you use is referred to as EZ determination, or EZ stereochemistry. Now, when you are asked questions about determining E and Z, you're not going to have to name the whole thing. You're just going to have to determine whether something is E or whether something is Z. All right, so are there questions about what's on this slide? Okay, so we're going to do some EZ determination, and then I'll give you a practice problem. Okay, so when we have E and Z, this is used to describe placement of R groups off tri and tetra substituted alkenes. So what we're going to do is we're going to look at the groups that are coming off of our vinylic carbons. So remember, the vinylic carbons are the carbons in the double bond. Okay, we're going to rank by priority by atomic number as either high or low. High is the higher atomic number, low is the lower atomic number. Okay, so let me show you what I mean by that and with doing this, and then we'll go to the actual E and Z. So you're going to have your vinylic pi bond, and then off of upper left, put an ethyl, bottom left, fluoro, upper right, hydrogen, bottom right, put an amine. Okay. So what you're going to do first is you're going to draw a line that bisects the pi bond, separating the left carbon, which is here, from the right carbon, which is there. Okay, so you're going to compare the groups off of the left carbon, the groups off of the right carbon. Okay. Fluorine is atomic number 9. Carbon is atomic number 6. So the fluorine is high, the carbon is low. On the right side, nitrogen is atomic number 7, hydrogen atomic number 1, low, high. Then what you do is you draw a line through the carbon atoms like this. So you kind of end up with like a crosshairs thing. And you look at the relative placement of two like groups. So you could do low and low or high and high. Okay. In this case, high and high are on the same side. Okay, so that's given Z. If high and high were on opposite sides, it's E. Okay. And just like with R and S, if the first atom in the group can't be used to gauge priority, you look at what it's bonded to. So if this had been a carbon and this had been a carbon, then you would have looked to see what else those carbons had been attached to. So if there aren't any objections, I'm going to give you 2 practice problems to determine E and Z priority. Okay. Does anybody need this slide? Okay. So draw your alkene. Now don't panic then if you see the alkene like this. I'm just drawing it parallel or like horizontally to make the R and S, or sorry, EZ easier. E and Z less difficult to assign. Okay, so up here, put a 1 carbon alcohol. Down here, put a tertiary butyl group, a propylene group, and then a propyl group. Okay. Then down on the second example, fluorine, hydrogen. Up here, we're going to put an ether, and down here, a tertiary butyl. So you guys work on those for a while. I'm gonna dump out my cold coffee. I'll be right back. Okay, does anybody need more time? Okay, I'm gonna move this over, so I don't think I gave myself enough room. Okay, so again, the first thing we're gonna do is bisect the pi bond and look at the 2 carbons. So the first atom up here is a carbon. Down here we have a carbon. So we have two groups that are tied. So we look at the things bonded to this carbon atom. That carbon is bonded to two hydrogens, because it's sp3, and an oxygen. This carbon down here is in this tertiary butyl group, carbon, carbon, carbon. Oxygen is higher than carbon, so this side is high, low. Carbon and carbon. Okay, they're tied. The top carbon is bonded to hydrogen, hydrogen, carbon. The bottom carbon is bonded to hydrogen, hydrogen, carbon. So these two carbons and the groups associated with them, or the atoms associated with them, can't be used to distinguish. So you move on to this carbon. Carbon to carbon. So those are the same. The second carbon is bonded to hydrogen, hydrogen, carbon, because it's sp3. This carbon is bonded to a hydrogen and then double bonded to carbon, so those carbons count twice. Two carbons is better than just one. High, low. Okay, now you draw your dashed line to make the crosshairs through the carbons. The highs are on opposite sides. So this is E. This side, let's first bisect pi bond. Low, fluorine is high. Carbon here and a carbon here. So we have to look at the groups off the carbon. Hydrogen, hydrogen, oxygen due to the ether. This carbon in the tertiary butyl group has 3 carbons. Oxygen is higher than carbon. High, low. Make your crosshairs. These are on the same side of the green line, high and high. This one is Z. Are there any questions about either of these two before we talk a little bit more about stability? Okay. All right. So we've already said that in terms of alkenes, mono substituted is less stable than di substituted, which is less stable than tri substituted, which is less stable than tetra substituted. But in the di substituted category, you have the cis and trans isomers. So we're going to compare the stability of cis and trans isomers. So cis would look like this, trans like that. Now I'm going to use circles to draw the methyl groups in terms of the size. Let me draw this a little bit over here. So when you look at these two, cis versus trans, these two large groups are having to share space. So the cis isomer has steric strain. The trans isomer has the large groups far apart. So this has no steric strain. So trans is more stable than cis. Oops. Okay. But unlike when we were looking at the Newman projections, and you could turn and go to various conformations within like a linear alkane like butane, you cannot interconvert these by rotation. Okay, so cis cannot become trans, and trans can't become cis by rotation. Okay. And the reason that is that the pi bond locks the R groups in place. You have no free rotation around pi bonds. Single bonds you do. Sigma bonds you can freely rotate, but pi bonds you cannot. The only way to go from cis to trans, this would be for rotation. The only way you could do this would be through a reaction in which you break bonds and then make them. Sorry. My robot vacuum is making a lot of noise. Okay. All right. So, are there any questions about the steric strain before I show you how we know that? Okay. So what we would say is, how do we know, or what is the evidence? How do we know that a trans alkene is more stable than a cis alkene? And the answer to that is we do perform a combustion reaction in a calorimeter. Okay, now you did calorimetry in 101. It's where you do a reaction inside of nesting coffee cups, and you measure the change in the temperature of the solution as the reaction proceeds. Now, you can't perform a combustion reaction inside coffee cups because you'll melt the styrofoam, but you can do combustion reactions in what's called a bomb calorimeter. And so if you take the transalkene and you react it with 6 moles of oxygen, you're going to make 4 moles of carbon dioxide and 4 moles of water. This reaction is exothermic and releases 2682 kilojoules per mole. Now don't worry about the unit, the number. Just know that it's exothermic. If you take the cis alkene and you perform the same reaction, what you can see is, because we have the same molecular formula, but different connections in space, we end up with the same products, but we release a different amount of heat, minus 2686 kilojoules. So there's a difference over here of 4 kilojoules. This released more energy, The top one released less energy. So up here, we would say less energy released. More energy released. This only really then makes sense when you put it on an energy level diagram. So this is going to be the enthalpy. And we're going to put down here is our products. So this is the 4 CO2 and the 4 waters. Okay. These values represent how much higher than the products the reactant energies are. Okay, so this difference here as an absolute value is 2682. This difference here is 2686. So if we write down the reactants, trans versus cis, you can see that this difference here is the stability. Trans is more stable than cis because less energy is released in the combustion reaction. Okay. So as you go, it's a little bit more difficult when the molecules aren't exactly the same because you have to normalize the enthalpy diagram. But as you go from mono to di to tri to tetra, the number of R groups off your sp2 vinyl carbons helps stabilize the pi bond. Now the theory behind this is based in molecular orbital theory. And we're not going to go into a lot of details, but it's an idea, it's an MO, molecular orbital theory idea called hyperconjugation. But you just need to know relative order. So you would need to know that mono is going to, substituted alkene would be less stable than a cis alkene, which is less stable than a trans alkene, which is less stable than a tri-substituted alkene, which is less stable than a tetra-substituted alkene. So if you were given a set of alkenes, you would need to be able to either rank them or pick the highest energy or lowest energy alkene, or most stable or least stable alkene based on the number or the degree of substitution. Okay, are there any questions about this beginning part of chapter 8, how to name alkenes, stability of alkenes, E and Z, cis and trans, anything before we move on to the second half, which are the mechanisms of elimination? Okay. So this is section 8.6. Mechanisms of elimination. Okay, so I'm just going to draw, I'm not going to include the reaction arrows, I'm just going to draw the components, and we're going to start this as close to the way we started our analysis of substitution as possible. Okay. So we're going to have a substrate that has a leaving group. Okay. Now we're going to react it with a base. that may or may not be charged. And what we're going to form is an alkene plus the base attached. Oh, nope, that's not right. The base is going to have a proton plus the leaving group. Those are going to be the things. It's driving me crazy. Sorry. Gosh. Okay. All right. So the substrate has a leaving group. Then you have a base to make an alkene, a protonated base, and leaving group will be gone. Okay. So just like we looked at before, we're going to have to consider our 4 characteristics. Okay. We have to look at our substrate, but we can no longer use methyl substrates because methyl substrates only have 1 carbon. And our alkene has to, in order to make a pi bond between 2 carbons, the substrate has to have 2 carbons. So our substrates are primary, secondary, or tertiary. Okay. You have to have a leaving group. Okay. And the same rules apply for elimination as in substitution. So if something was a bad leaving group in substitution, like the OH group, it's a bad leaving group for elimination. And you'd have to fix it prior to performing the elimination reaction. Okay, now in the substitution reaction, the third consideration was the leaving group, or the base, nucleophile. In elimination, it's the base. So it can either be lone pairs and neutral, or lone pairs and negative charges. Okay, now over here, this is where things are going to get a little dicey. I want you to write a note. Just because something is a good nucleophile doesn't mean it's a good base. Okay. So you have to consider the ability to act as a nucleophile independently from the ability to act as a base. And that goes back to the jobs. So the nucleophile performs attacks on carbocations or partially positive carbons. Bases grab protons. Those are 2 totally different jobs. So something might be a really, really good nucleophile, but a crappy base. Okay. So the nice thing is because the base nucleophile bit gives you one more thing to think about in terms of elimination. You will have solvents, but the reactions aren't picky. The elimination reactions aren't picky. Substitution reactions are very picky about the solvent. Okay. I'm going to see if I can move this down so I can leave some of it up. Oh gosh, this works great. Okay. So the next part of this, just like in substitution, all or both elimination reactions or elimination pathways involve 2 steps. Okay. Okay. Loss of the leaving group. proton transfer. If the steps occur at the same time, so in one step, then you're going to need an E2 elimination. So again, so this 2 is a kinetic 2, so it's bimolecular. So the rate of this reaction is going to be equal to the rate constant times the concentration of the substrate times the concentration of the base. Right. If the steps occur in sequence, in 2 steps, loss of the leaving group, then proton transfer, it's E1, with the rate equal to the rate constant times the concentration of the substrate. Okay, so these rate laws give you the molecularity of the elimination reaction, just like they gave you the molecularity of the substitution reaction. Okay, one step is going to require a collision as your slow step. If you have a 2-step, you would have to go substrate to carbocation and then proton transfer. If you have anything that goes through a carbocation, you have to consider rearrangement. Okay. So we're going to start with the E2 mechanism if there are no questions about some of this introductory stuff before we go on. Okay. Back up so I can get a little bit extra room over here. Okay. All right. So this is section 8.7. E2 mechanism. Remember the E2 mechanism, this is molecularity, so it's a bimolecular reaction which requires a collision occurring in one step. So until we identify bases, I'm just going to write this in a very simple way, and then we'll do a little bit more, we'll go into a little bit more detail. Okay, so I want you to draw your substrate really basic, like this. And of course, you'd know that this is a good leaving group. Okay. But I want you to indicate one specific proton. Okay. The carbon with the leaving group is alpha. Okay. The carbons that are next door are beta. So you could draw your hydrogen up here, you could draw your hydrogen over here. They're all equivalent beta positions, but I'm just using over here so I have a little bit more room. So alpha has to have the leaving group. Beta must have a proton or a hydrogen atom. Okay. Then we're going to have our base. Okay. Now, in this reaction, you have to have 3 arrows. Okay. The base has to come and grab the proton. the sigma electrons fall down to become pi electrons, and the leaving group leaves. Okay. So we have to grab a proton, sigma electrons become pi electrons, and then our leaving group breaks off. Okay. All at one time. Okay. Alpha and beta now have a pi bond between them. And alpha still has those two other methyl groups. And then we have our base that's bonded to the hydrogen, and we have our leaving group gone. All right. Questions about the arrows and what they represent? I want you to put a note. Oops, come on, purple. Substrate identity was the easiest way to tell SN2 from SN1. Okay. If you wanted an SN2 mechanism, you had to have a methyl or a primary substrate. Secondary in some circumstances, tertiary would never work. SN1, you needed to go through a carbocation intermediate, so you needed a secondary or a tertiary substrate. Okay. The same is not true for elimination. Okay, you cannot use substrate identity to automatically say E1 or E2, like you could have in substitution. And I'll show you why. Probably giving somebody a headache, I'm sorry. Okay, so I'm going to write substitution here. And I'm going to write elimination here. And what I'm talking about is an SN2 substitution and an E2 substitution or elimination. Okay. So I want you to draw a tertiary substrate. Okay. Which you know won't go by SN2. You know it won't happen. Okay. But I just need you to draw it for completion. Now, a really, really good base is hydroxide. Okay. So in substitution, we need nucleophilic attack. And we usually use a strong nucleophile because we have to get to a partially positive carbon. But if you consider the size of these methyl groups, this hydroxide can't get to the partially positive carbon. Right? It can't get in there to even do the nucleophilic attack. Okay. Right. So you have steric hindrance prevents the SN2 reaction. Okay. Now I want you to draw the same substrate on, so you would write no. Okay. But you knew that already. Same substrate. Okay, but now what I want you to do, instead of showing these as spatial and steric issues, I want you to draw them as methyl groups with all the hydrogens shown. Okay. And your hydroxide compound. Okay. All right. So in elimination, we need our base to grab a proton. There's 9 of them on here, and they're all on the outside. So this hydroxide, as a base, can pull any of these protons off, and the reaction will proceed. Just, okay, so grab a proton, anyone you want. The sigma electrons have to fall down to become pi electrons. The leaving group has to leave. So when it comes to E2 eliminations, primary, secondary, and tertiary will work. And actually, the rate increases in this direction. These are fast eliminations. These are slower. And all it has to do with is the number of hydrogens available. The probability of finding 1 in 9 is higher than the probability of finding 1 in 3. Because you have the molecules, this hydroxide would see no protons here, and then finally find one over here. This thing can bump anywhere and the reaction will proceed. Okay. Questions? Okay. Trying to think if I want you to practice drawing the mechanism with all the compounds listed. So I want you to draw the arrows for an E2 mechanism under the following conditions. Okay, so there's your base, methoxide. Okay. Wait a minute. Just make it like this. Okay, but there is a CH3 group here. Okay, and show your product. Actually, I lied. Sorry. Make this the CH3 group up here. It'll make it easier because you have to make the trans product. It won't be trans. Never mind. It was fine the way it was. I shouldn't make stuff up as I go. Okay, so in this one, these are pretty simple to draw. You grab the proton, take the proton electrons over, or sorry, the sigma electrons, make them pi electrons, lose your leaving group. So what you would have at the end is this alkene, and that would have been the alkene you made from the first way I drew it. I don't know why I had a brain spasm. Methanol, and then you would have bromide. Okay. So E2 mechanisms are one step. I'm just going to show it as being exothermic. One transition state, no intermediates. Okay. All right, so now what we're going to do with E2 is we're going to talk about something that's called regioselectivity. Okay. And that's going to lead to something that we call a product mixture, which is when you get more than one product in your reactant, or sorry, in your reaction. It's called regioselectivity. Oh gosh, sorry y'all. And regioselectivity is going to be described in this instance as placement of the pi bond. And so what we're going to draw is this substrate. So it's a tertiary alkyl halide. 2-bromo, 2-methyl butane. It's achiral, thankfully, so we don't have to do R or S because we have 2 methyl groups here. So it's 2-bromo, 2-methyl butane. But now if you look at this, here's alpha, the carbon with the leaving group. And here's beta, beta, and beta. But these are different kinds of beta carbons. This is a primary beta carbon because it's attached to one other carbon. This one down here is primary. This one down here is secondary. Okay. I'm actually going to make this green. So what we have to consider, if we have different beta hydrogens, or different beta carbons have different beta hydrogens. Okay. So if we remove with a base, I'm not going to show the mechanism, but if we remove from here, then we're going to make a product that looks like this. Okay. If we pull the proton from here, we're going to make the product in green. So this is a di-substituted alkene, and this is a tri-substituted alkene. So they're not equally stable. This alkene that's tri-substituted, you can see 1, 2, 3 groups versus here only 2 groups. The tri-substituted alkene is more stable than the di-substituted alkene. Okay. Now, if you use a small base, like small in size, like hydroxide, methoxide, OCH3, or ethoxide, OCH2CH3, then this is your major product. Okay. This major product, the higher substituted alkene, that's called the Zaitsev product. You still get some of this, but it's considered a minor product. So if the purpose was to make this alkene, you wouldn't use a small base, because your small base is going to cause the formation of the Zaitsev product, the more highly substituted alkene. Okay. Now that consideration is called Zaitsev's rule. Zaitsev's rule, Zaitsev's rule tells you that in E2 eliminations, the major product is always the more substituted or the more highly substituted alkene. So the tri-substituted is highly substituted relative to the di-substituted, but this consideration, following Zaitsev's rule, only works if you use a small base. Okay, and like I said, there, hydroxide, methoxide is considered small, and ethoxide. I'm hoping by now you're seeing that negatively charged oxygen species are really, really good bases. Okay. Right, are there questions about Zaitsev's rule? What you might be wondering, but just don't want to say because it means more mechanisms, is can you switch this and make, are there any conditions where the di-substituted alkene will be the major product? Yes. Okay, so we're going to use the same substrate. But now what we're going to use, instead of a small base, is we're going to use with what we call a big, bulky base. Okay. Big, bulky bases are going to make the di-substituted product will be your major product. You'll still make some of the tri-substituted product, but it's going to be minor. Okay, so you can elevate the concentration of the di-substituted product just by taking a big bulky base. This major product is called the Hofmann product. So small bases give you the Zaitsev product, big bulky bases give you the Hofmann product in E2 eliminations. Okay. So big bulky bases, there's three that are commonly used. The first is tertiary butoxide. It's TBUO. The second is called diisopropylamine, diisopropylamine. Like that. And the last one is called triethylamine. Like that. The one that is most common is tertiary butoxide. And in an E2 elimination, the big bulky bases are going to make the Hoffman product dominating. I'm going to give you 2 examples that I want you to work on and see if you can come up with the major product. We'll do them one at a time. So we'll do one and then we'll do the other. Predict the major product. I want you to use E2. Okay, so just like in substitution, your bases are often going to come from salts. So sodium methoxide is the source of the base in this case. Okay, so I want you to determine the major product and draw it. Okay, so my suggestion would be that you draw both products and then come back to the identity of the base to make a final decision. So for this one, I would come in and write, okay, here is my alpha carbon, and I'm going to end up with a beta carbon off the ring and two identical, essentially, beta carbons inside the ring. Okay. If you pull from the blue beta carbon, your product is going to look like this. Okay. If you pull from a green beta carbon, your product is going to look like that. Okay. Then count the number of R groups off of the vinylic carbon. So these are both hydrogens up here. There's an R group on this side and an R group on this side. So this is a di-substituted product. The green pi bond has an R group here, an R group here, and an R group here. There's 3 allylic carbons, so this is tri-substituted. So there is chemistry going on in here. We end up with 2 different substituted alkenes. Okay. Then go back and determine whether or not that base is little or big. Methoxide is a little base, which makes the Zaitsev product as major product, which would be this one right here. If you want to see the mechanism for that, you would just draw a hydrogen on a beta carbon. Take your base, grab the proton, sigmas become pi's, lose your leaving group. And you would end up with your tri-substituted alkene, methanol, and bromide. Okay. Are there any questions about regioselectivity? Do you want another practice problem to identify the major product, or do you want to move on to stereoselectivity? Does anybody have a vote? Practice, move on. Okay, we'll move up. Okay. All right. Karen said another practice problem. Okay. Oops. Okay, so this will be the last thing we do today. There's not really enough time to go into stereoselectivity, so that's fine. Okay, so again, we have a tertiary alkyl halide, thankfully achiral, but you should be able to name it 2-iodo-2-methylpentane. Right, so you have an alpha carbon. Let's see, I don't have another color. You have an alpha carbon with a leaving group. This beta carbon is exactly the same as this beta carbon. They're both methyl carbons in terms of they're both primary. The green one in here is secondary. It doesn't matter which of the two beta positions you draw from, or you pull from, because the product will be the same. You might not draw it the same, but the product would be the same. So if you pulled from blue beta 1, you would draw this. If you drew, I would draw that. If I pulled from beta 2, I would draw that. But because of free rotation here, these two things are the same. Okay. If I pull from the green one, the product I make looks like this. And then I would have to identify the type of alkene I have. So there are 2 R groups here. So this is disubstituted. 1, 2, 3, trisubstituted. Okay. I go back, look at my base, and it's big, which is a Hoffman selective reaction condition. So the disubstituted alkene would be your major product. Okay. The mechanism then, you would have your tertiary butoxide, grab a proton, electrons fall to the pi bond, the iodide leaves. Then you would have tertiary butanol and iodide, like that. So to kind of summarize what we did today, we talked about you should be able to name alkenes, do cis and trans alkenes, E and Z designation. Know that E2 mechanisms can work on primary, secondary, and tertiary substrates, and know how to situate your reaction so that you get either a Zaitsev product or a Hoffman product. We did a lot today. So we likely will use most, if not all, of tomorrow on 8, but there's a possibility we'll get into 9. In the meantime, if you need anything, definitely let me know. Otherwise, I will see you tomorrow. Okay? You guys were very quiet today. Kind of words.
Thank you.
Yeah, you're welcome. I'll talk to y'all soon.
Thank you.
Yep, you're welcome. Bye. Oh, Thomas, I just saw your question. Today, Tuesday? If you're available during office hours tonight, I'm happy to talk about the test with you. tonight. Otherwise, we'll just find a time that works. Or we can do it by email. It's your choice. Okay. All right. Alrighty, I'll see you guys. If you need anything, office hours are tonight. Otherwise, I'll see you tomorrow. Okay, bye.